Kinetic molecular theory. So what is it? Well, in the kinetic molecular theory, we are assuming that gases consist of very, very tiny particles, and those particles are so small compared with the distance between them that the volume of those particles are really negligible. What's actually happening is these particles are in constant random motion, and when they collide with the walls of the container, this causes pressure. We also assume that there is no attraction between particles and no repulsion of particles. So we assume that there's no force of attraction or force of repulsion causing these molecules to stick together or be not attracted to one another. Last thing we're assuming is that the average kinetic energy of all the gas particles is directly proportional to the temperature of the gas measured in Kelvin. So let's talk about the velocity of gas molecules. Molecules, again, have a given range of speeds. The peaks show that the average speed of the gas molecule at a given temperature. For example, we have right here, this makes up the average speed of 400 meters per second at this given temperature of 25 degrees Celsius. This right here measures the average speed of 800 when the gas is at 1000 degrees Celsius. So what is the meaning of temperature? The meaning of temperature is the average kinetic energy of those particles in a sample matter. The equation for kinetic energy of a mole of gas is equated to 3/2 times R times T. R is a constant, which is 8.31 joules per mole Kelvin. The units of kinetic energy is equated to joules per mole. Joules is a unit of energy. The exact relationship between temperature and kinetic energy is very simple. Well, if we take kinetic energy and we divide it by T, we know that 3/2 R is equated to this constant. So how are they related? If kinetic energy goes up, so does temperature. And if temperature increases, so does the kinetic energy. So they are directly proportional. Here's an example problem. What is the average kinetic energy of 1 mole of hydrogen gas at 40 degrees Celsius? Well, if you plug it into 3/2 R times T, you should get 3,901 joules per 1 mole. What about if we asked about the average kinetic energy of 1 mole of nitrogen gas at 40 degrees Celsius? Well, you should get the same value. So why are they the same? Well, they're the same because they have the same temperature, and that is the definition of temperature, the average kinetic energy. So if they're at the same temperature, they're going to have the same kinetic energy. The root mean square velocity is the speed of these molecules, okay? And it tells us, on average, how fast these particles are traveling at a given particular temperature. The root mean square velocity is the square root of the average of the squares of the gas particle velocity. Because molecules within a given gas have a different velocity, we account for the average using this equation. We have the square root 3 times R times T divided by M. So what does all this mean? 3 is a number, R is a constant, T is measured in Kelvin, M is the molar mass in kilograms, and these root mean square have units of meters per second. So how are these all related? Well, just like kinetic energy is related to temperature, it also is related to the speed of these molecules. So as temperature increases, the speed of these molecules increases as well. But the speed of these molecules is inversely related to its mass. In other words, if you have a lighter gas, its speed is going to be a lot faster than a heavier gas, and vice versa. Here's an example problem. What is the root mean square velocity of 1 mole of hydrogen gas at 40 degrees Celsius? Well, if you plug it into the equation, remember that 1 mole has to be in kilograms, and this has to be in Kelvin. If you plug it into the equation, you should get 1,975 meters per second. What about the root mean square velocity of 1 mole of nitrogen gas at 40 degrees Celsius? Well, as expected, nitrogen gas is a lot heavier than hydrogen gas, so therefore it should be a lot slower. And in this case, when we plug it in, it's 528 meters per second. So why are they different? Even though they're at the same temperature, they are traveling at different speeds because they have different masses. Difference between diffusion and effusion has to do with, again, the speed and the kinetic energy, so on and so forth. But when we talk about diffusion, we're talking about how quickly we can mix gas together. Effusion has to do with the term of how gases pass through a tiny small hole and travels again. So it's having to do with mixture, but it's having to do with how gases and where they are. Graham's law of effusion states that the relative rates of effusion of two gases at the same temperature and pressure are given by the inverse ratio of the square roots of their masses of the gas particles. So here's the equation. Okay, we have the rate of gas 1 over the rate of gas 2 equals the molar mass, the square root of the molar mass of gas 2 divided by the square root of the molar mass of gas 1. The number produced tells you how many times greater the rate of effusion is for gas 1. Okay, so no units will be used in this equation. Once you get a number, it's just going to be a whole number, in other words. Okay, and last thing we need to mention here is that heavier molecules obviously effuse and diffuse a lot slower than lighter molecules, based on the previous equation. So, why do heavier molecules effuse and diffuse more slowly? Well, it's very simple. It's consistent with the kinetic molecular model, which states that the velocity is inversely related to its mass. So is this case so simple with diffusion? Yes. Diffusion and effusion are showing how things move and how things are mixing. So they have to do with the same equation. It doesn't matter if we say effuse or diffuse, they're going to effuse or diffuse at the same rate, using the same equation. Here's an example. What is the rate of effusion of 1 mole of hydrogen gas to 1 mole of nitrogen gas at 40 degrees Celsius? Which is faster and how much? Well, if you plug it into the equation, you get rate of effusion for gas 1 over rate of effusion for gas 2 equals the square root of the molar mass of gas 2 divided by the square root of the molar mass of gas 1. If we plug that in, we get the square root of 28 divided by the square root of 2, which equals 3.74. So what does this mean? This means that hydrogen, which is gas 1 in this case, effuses 3.74 times faster than nitrogen gas. So what do the numbers mean? So if the number is greater than 1, then the first gas effuses or diffuses faster that many times than that number compared to the second gas. If the number is less than 1, then that means that the first gas diffuses a lot slower, that many times that number compared to the second gas.